Okay, so where were we? I think we were talking about range, and I was saying that range is different than the domain. The domain, as you see, we can plug in any x value and come up with a y with a corresponding f of x or y value. But the y values, and remember, every time we look at f of x, we can also think about it as y. The y values for the greatest integer function are different. Notice that we never get any intermittent or any values that are between these integers. And so that should let you know that and remember the definition of the greatest integer function is that your answer is going to be an integer. So that should really tell us that our range is going to be all integers. Does that kind of make sense, guys? I hope so. Let's take a look at another example. If we check out this one, so again, we're going to be dealing with a step function, but this one we won't have the greatest integer function to deal with. We're actually going to have a real life situation. So a cell phone company charges 45 cents per minute or any fraction thereof for exceeding the allotted minutes on each plan. Draw a graph that represents this situation. So let's kind of break it down. You've got a cell phone plan. You pay for a certain amount of minutes, then you've got overage. If you go over 1 second, they are charging you as if you spent a minute. If you go over 59 seconds, they're charging you for a minute. That's 45 cents. If you go over 1 minute by 1 minute and 1 second, how much do you think they're charging you? Yes, they're charging you as if you went over for 2 minutes. So when we think about this situation, we know, and we can think of it this way. If x, let's let x, this column will be x, and this column will be the charge, just call it y, and I'll put the charge that you're going to be charged. We know that the charge from as soon as you get above 0 seconds, right, all the way up to 60 seconds, or let's just do it in terms of minute. If you get from 0 to 1 whole minute, and that's including a minute, if x is between there, you're going to be charged at 45 cents, all right? And then if you go on from 1, as soon as you are above 1 and up to and including 2, you got it. You're going to be charged 45 cents twice, which is 90 cents. You guys see the pattern. So I'm going to fill out this chart and fill it out like that. And the next thing we need to do is use our graph over here to actually plug in the information. So you can see that for several values of x, we're going to have a 45-cent charge. Then for several values of x, we'll have a 90-cent charge. So let's go ahead and put our axis in. Okay, shifting the things a little bit, but here's what we're looking at. We have the charge listed down here as the possible choices. And I know somebody's going to ask, but from here to here is 45. From here to here would be 90, then from here to here is 135, and then to here is $1.80, and you see the process. And over here we have the minutes over. So this is how you're going to get your overage charge. I'm going to use purple because I was told that I don't use enough different colors by one of your classmates. We won't name them. And so as long as the person is over a minute, so at 0, we're going to have an open circle. But as long as you're over up to a minute, you're going to be charged 45 cents up to that minute. But as soon as you go over that minute, as soon as your time over is beyond that minute, your pricing props up to another 45 cents, which is going to give you, remember this is 90, which is going to give you 90. So at 1 minute, you're not at 90, but everything after 1 minute, you've paid 90 cents all the way up until 2 minutes. And then again, one more 45 cent is being, or another 45 cents is being added onto your bill as soon as you go over 2 minutes, not at 2 minutes. So I've got an open circle. You guys see what I'm doing? You get where I'm going. And you see that this is a step function. Again, not exactly the greatest integer function. In a way, it's kind of flip-flopped. And we could talk about ways to describe this at another time. So this is what we have. This is our situation. And so we've drawn it. We've drawn the graph that represents the situation. Yay. Let's go on to this next example, example 3. Here we have a different function altogether. So we're moving out of the realm of the step functions and we're looking at something called the absolute value function. We talked about the absolute value function before, and we recognize that we're going to have a V shape, some kind of V shape. Sometimes it can be upside down, but for the most part, we're always looking for a V shape. So here's what we do. We're going to put this will be our X column. There's that purple. And we'll use this part, X minus 4, the absolute value of X minus 4, to be our f of x, or also known as our y column. And then we're going to graph our values here. So let's go ahead and get started. I'll use orange and see how that goes. So I'm going to just plug in some numbers that I think are going to be pretty cool to use. I'm going to start with, let's say, -2. So at -2, when I plug -2 into this expression or this equation, I get -2 here, -4 is going to give me a -6, the absolute value of which is a +6. Here, if I do -1, I'm going to get a +5. Plugging 0 in, I get a +4. If I plug 1 in, I get 3. If I plug 2 in, I get 2. If I plug 3 in, I get 1. If I plug 4 in, I get 0. Let's keep going. Let's do a few more. Because what I want to see when I create this chart is I want to see a turn. And that turn is going to look like my y values or my f of x values are going to start to repeat. So that lets me know that I have a bend or a turn. So if I continue, let's say I put 5 in. When I put 5 in, 5 minus 4 is 1. The absolute value of 1 is 1. There's my turn. 6. When I put 6 in, 6 minus 4 is 2. Absolute value of which is 2. 7. And you see we get 3. And I can continue, and you can see the numbers are going down, and then they're going to go back up. So let's check out what this looks like on our graph. So I could start at a -2, which is right here, and I need to go up to 6. I'm not sure if we have enough space, but we'll improvise. 1, 2, 3, 4, 5, 6. Is that 6 really? Yay! So at -2, I'm at +6. At -1, I'm at a +5. Okay, and at 0. No, I'm sorry. Yeah, at 0, I'm at 4. And no, let's use that color. Yeah, orange. At 0, I'm at 4. At 1, I'm at 3. At 2, I'm at 2. At 3, I'm at 1. At 3, I'm at 1. At 4, I'm at 0. And then the bounce begins. At 5, I'm at 1. At 6, I'm back up to 2, and et cetera, et cetera. And so what we see is that we're going to connect the dots along that line, and we get that telltale V symbol, which we know we're dealing with, sorry for this lack of beautiful line, we know we're dealing with an absolute value equation. And so that's what they often look like. So here's one thing that I want you guys to start thinking about as you guys think about functions. So this would be considered the parent function to this, right? Because this function here is of the same form. But notice, what's the difference between this graph, which would have had its bend, let's say at the origin, and this one? Notice that it is shifted over 4 to the right. This -4 is giving us some indication about that shifting, and that's something that we'll talk about at a later time. Let's take a look. The final example that we have is something called a piecewise function, and it looks kind of crazy. But, I think we missed something here. It says state the domain and range. My bad, Chabelitos. For us, the domain is all reals. And we can see that we can put any old x value in there and we're good to go. The range, however, is different. Notice that we have every y value, but this bounce keeps y from ever being negative, which makes total sense because y, or f of x, is equal to the absolute value. So it is all positive numbers, or all positive reals, you could say. Or you can say all numbers such that those numbers are greater than, let me do greater than or equal to, so y such that y is greater than or equal to 0. So y can be equal to 0, as we saw. I can't get this to stop shaking. 0, come on, write for me. It doesn't want to write. Let's do it this way. Y is greater than or equal to 0. That's what I'm trying to do. All right, so that's our range. Let's look at this one. So a piecewise defined function is a function. Sometimes I call them Frankenstein functions, right? Frankenstein to create, or what would be a better analogy? Something where, you guys could tell me, something where you take part of one thing, part of another thing, and you stick it together. That's kind of what that's exactly what piecewise functions are. So basically, and here would be a great place to use two colors. Perhaps I'll use orange and purple. All right. So that equation we're going to draw in purple, and this equation we will draw, this one we'll draw in purple, orange, and this one we'll draw in purple. So we're going to graph, so basically for the purple, for the orange part, my bad, we're graphing f of x is equal to negative 2x. And for the purple part, we're going to graph f of x is equal to x plus 3. This is totally reasonable. You guys can do it. Remember, think of it as y is equal to x plus 3. Think of the other one as y is equal to negative 2x. You guys can graph that. However, there's one bit of information that we overlooked. When we graph these, we do need to pay attention to the domain that is restricting our graph. So this particular part of the equation where we're graphing y equals negative 2x is only to be done as long as x is greater than 1. Not when x is equal to 1, but when x is greater than 1. And this other portion of our graph, where the purple graph, let's call it, this portion is only supposed to be done when x is less than or equal to 1. So I'm going to do purple first because purple is referring to x values all back here, right? Because those are x values that are less than. Okay, so here's what I'm going to do. I'm actually going to just plug it in and plot my points as I go. So x plus 3. Well, let's let x be negative. Well, first of all, I know that each of these are lines. I could graph them as lines separately. Let me do it that way instead of doing it what I just started doing. So if I graph this by itself, just forgetting about this little restriction here, I would have, you guys would go to the center here because that's the y-intercept, and you would tell me if you rise 2, you got to go back 1, or if you go down 2, you go to the right 1. And everybody would be satisfied with this as a graph because that's what it is. But then when we go back and we look a little bit further, we have this restriction. It says, yeah, I only want this when x is greater than 1. Therefore, all of this part of the graph is unnecessary. We want to start this graph when x is greater than 1. So this graph does this, and I'm literally going to go back and erase all of this, okay? And I'm going to do this so that I'm going to also do something special here where I'm going to put an open circle right here. Think about why there's an open circle here. Is this function defined? Is this portion of the piecewise function defined at 1? No. It says as long as x is greater than 1. So I have an open circle there. Now I'm going to go back and I'm going to think about this equation. Let's use my purple pen. X plus 3, we know that the y-intercept would be 3, which is right here. And we know that the rise over run is 1, up 1 over 1, up 1 over 1, or back 1, down 1, back 1, down 1, back 1. So here's my beautiful line. But as you know, with the last one, I'm ignoring something. I'm ignoring this restriction. It said this is true only for when x is less than or equal to 1. So equal to 1 is cool. I'm going to put a solid dot there. Less than 1 is also cool. So here are all the x values less than 1. This graph exists all back here, but it does not exist up here. So I need to go ahead and grab my eraser. And sometimes my eraser is funny and it likes to erase more than I want. But it kind of did. All right, but that's okay. So this is what a piecewise function looks like. You need to graph each piece. Sometimes you need to have your eraser handy so you fall within the restricted allotted space or the allotted domain. My time is running out. This is becoming longer than I want it to be. Here's our assignment. Know that I can't wait to see you guys tomorrow, and I look forward to talking to you about these 3 cool functions when we see each other. Take it easy.